Good morning, everybody. So we are into programming, and yesterday we partly solved one of the exercise problems, namely problem 2.4. Okay. So any questions? Do you have any doubt? Any questions? Okay. So far we solved the displacement, you know, and the problem now next asks you what is the value of reaction forces, what is the value of stresses, and for that you have to do further analysis. So u free is given, and you know that fixed DOF means that u will be otherwise zero, at least where that is degree of freedom is fixed, the displacement will be zero. As such, you can have u defined. Yeah, so actually the u is the universal u. You can have this in terms of zeros, and should be equal to number of nodes or number of degree of freedom. Yeah, so it should be 2 times number of nodes is number of degree of freedom and 1. So meaning that the dimension of u is like that. So you can now prob 24. So u will look like this. Yeah. So you have defined u as this 8 by 1, and this is because uh, there are total 8 excuse me, so there are total 8 degrees of freedom, and just hold on, just there's a urgent call, so I will just okay. So total, like you have u is displacements. So the size will be 8 by 1. This is a vector because there are 4 nodes, and out of which we know these guys u free, right? And u free, the degree of freedom, free degree of freedom is 578. So we can replace corresponding. So u free degree of freedom, right, is equal to u free, right? So we have assigned those values we have calculated, we put it here. So this will now give the complete picture. So if we run it, then if we write u, then you get those value assigned here. See, we got these values now. So our U is complete. Now next you can find out F. So if you want F will be simply equal to, and we have the K, big K, already we know the big K, yeah, and the K multiplied by U will give you F, right? So let's run it again, and this F now will give you the all the forces include the reaction forces. Reaction forces we want where the at the fixed degree of freedom, which is at 1, 2, 3, 4, and 6. So this is 1, right? This is 1, 2, at 3, 0, the 4, 5 is given, but 6 we have to find out. 7 is given, 8 was also given to be 0. So that means we got the reaction forces automatically, right? So this tells you at node number 1 in the direction of X, what is the reaction force? And this gives you about 1 kilonewton, but negative, meaning that in negative X direction. So we calculate the reaction forces. Yeah. So this has everything, forces, including reaction force. We got the, this is the displacement vector, and so on. So we got that. Now only thing now remains is what is the value of a strain, how to calculate the strain. Okay, now in order to know the strain, you have to know the rotational matrix. Yeah. Okay. And how do you do the rotational matrix? See, earlier we have done for this, while calculating the stiffness matrix, we calculated this cos, sine, and so on. So accordingly, we have to find out which all things we need. Every truss element has 2 nodes, and each node has 2 degrees of freedom, and finally we have to find out how the displacement is in the direction of the beam itself. Yeah. So meaning that you have the at every for every element we have to accordingly process, and let's say for okay, for I equal to 1 to number of elements, we are going to process that. Okay, and then do what? First we want to find out, we have already the cosine, sine, all kind of things. So we will make the same thing as this. So C, now we will have some other meaning of C. So we'll call, let's say C is equal to cos of angle J. In this case, we will say angle I. Okay, and sine is equal to S angle I. Yeah, where angle is universal angle that we have saved it. Yeah. Okay. So, and then we are going to make rotational matrix. So we can write R, which is rotational matrix, equal to zeros. Okay. And then we have 4 by 4, right? So 4 by 4 matrix, we know that. And here we can say R is equal to and we had cos minus sine and then sine and cos. Yeah. Sorry. Then we had 0 0. Then we had sine cos. Then 0 0. Then we had 0 0 0 0 cos minus sine and then 0 0 sine and cos. So this is the matrix. Okay. Now you do not need to actually even use this one, so because we are going to use inside this loop only, so no need. So this is rotational matrix, and this rotational matrix, what does it do? This you remember that if you want to find out the like it was a local, you remember we said global UG is equal to R times local, right? So it was something like this. Here local was we wrote in with theta equal to 0. So this was in a configuration where theta equal to 0 was there, and this one was the global, and for that we just multiplied by R and we got this one. Yeah. So here what we want to find out is this one. We want to find out the local one based on the global. Yeah. So for every, first we have, if you want to find out the global one, we can find out the local one. And local one is important because that gives you displacement in axial direction, and in the direction perpendicular to the axis. So axial direction displacement is important because that gives you idea what the strain is, and hence we want that. So that really means we can use the UL is equal to R inverse. Yeah. So R inverse and multiplied by UG. First we have to construct UG though. Okay, so what is the UG? Okay, so UG, let's say UG is equal to, now for the first element we have two nodes. So the values that we will find out from here. So these are the degree of freedom and all. So I'm going to just copy. Let's go from the I1, okay, because we are also using the I only. So no, so let's do this one because it has also the degree of freedom calculate. So let's do this. Okay. Okay, since programming is not a good idea to copy here from here and there, because there are some issues. Sometimes you know, so you have to replace, you have to check whether you are doing some everything right. So this ij, you put I here in one, in I, 1 in 2, in I, 1 2 degree of freedom in 1. So we get the degree of freedom, correct one. Okay, now UG equal to U, and we are copying all the values from the global, the universal one, the one which is the big U. From there we are finding out the displacement values. Okay, so U is equal to U, and then this what we have now. Once you have the U, and then after that we want to find out UL. So UL will be equal to inverse inverse of R and multiplied by UG. So we get UL. Okay, so same thing you can also write differently, so which is more efficient, you know. So instead of writing this, we can also write just R like this, R inverse like this, you know? So this is the same statement, you know. Okay, so now when you get UL, now this is in local file format, meaning that the first one will give you the axial. So du you can find out will be equal to ul3 minus ul3 minus ul1 is the displacement, axial displacement basically. Yeah, and then strain I. Yeah, so we can have strain and stresses here. So we can say strain equal to zeros and number of elements times 1, say, and similarly stress equal to zeros Same thing, number of elements. So that way we can save them. So a strain I is equal to du divided by length. I think length. Let us see how we are also saving the length actually. So LE, yeah, LE is the length. So LE LEI. So this gives you the strain, and then a stress as well. You can write a stress I will be equal to simply E multiplied by strain I. Yeah. So we got that. So we can now run it. Okay. So we got all. So we can see a strain. Okay. So there are three elements, and it shows the first one has 0.1414 times 10 to power minus 5. Second one has minus 0.05, and third is 0. Means the third element is not stressed for the obvious reason that it is free to move, because a roller joint. So if there is a roller joint, it can move very easily, so you don't it does not be stressed. Because of that, it is like that. And the first one is under tension, and the second is under compression, and this gives you the strain, and you can also have the stress. And stress, as you know, if you multiply it by just E, so it will just change the multiply the strain with the Young's modulus, and you get the stress value, and you are getting that. So you have calculated everything, so there is a different way of doing the same thing. So if you wanted, you could have written it a different way. More you do programming, more you know the tricks. You can the better way of program is to write a lot of functions and use a small files, just in one file. You can have multi-file programming in one. In the main one, you have just 3-4 lines, and all others can be functions, and you call the functions. So those kind of things can be done, and which is all depends on your style and how much you are into programming. Okay, remember that this MATLAB is a high level programming, meaning that there's a lot of things that goes on that we don't see. If you are if you want to make it faster, you don't have much control. But if you want to do some low level programming, you can use C, lower level. You can use C++, for example, and there you have a lot of control. You can compile it being fastest or the lightest, like that. And there you will have control over how much time it takes. Yeah. Also, this is interpreter based, and the C is the compiler is there, so it compiles, and you have the executive file, and code you will not see, but it will run. Any question, guys? Anything you did not understand? Any issues? Okay. So computer implementation was the next, and that we have actually covered. We will look at a few more problems, and I will also share with you this. Okay. Okay. Now, similarly, we have the problem number 23, and actually just today I converted this into MATLAB program. Although this Scilab and MATLAB both, in fact, Scilab is a copy of MATLAB. So I had these files from last year, which was in Scilab format. So I converted that into MATLAB. And here the problem is like this. So you have four members. These are the node number 1, 2, 3, and 4. And then there is members 1 to 4, then 3 to 4, and then 2 to 3, and there's another member from 2, 2 to 4. Yeah, and then there is at 3 in positive x direction, there is a force, and then you have to do the analysis. The values are given, and you know the same thing we have been doing, but now you see that we are finding out L2 differently. We just see vector multiplication. You see, so this is like a dot product we are doing. Yeah. So rest is the same. Another thing you will see that instead of writing cos square theta, sin square theta, we are using the local k, which has 1, minus 1, minus 1, 1, and then we multiply with the rotational matrix. Yeah. So here we are using kr equal to rotate k. Yeah, and then we are giving the rotational angle here, ke, and length, and rotate k I have written as a function, so which is given at the end. So this is rotate kc, and what it does, it has rotational matrix defined. So we have cos sine 0 0 minus sine cos 0 0. If you see here, what we have is earlier what I wrote had minus here. Yeah, but finally when we are writing here, so see how we are writing. Earlier when we wrote r came here and r inverse came here, but here you see r inverse is coming here. R and r transpose are the same in this case. If you inverse of this will be equal to transpose of this only. Okay, so hence don't be confused, the same thing. So many times finally what you write here will be the same. Yeah, so it is not that it's different, it is the same thing. Okay, and you have this k r and k divided by length. So probably length is not multiplied there, most likely, because just say this is k only. Just a minute, guys. Do divide by length, that is the length. So we are calling it from here. So first K and K value A over L. Okay, so it's just assuming L equal to 1. So yeah, so actual length you are going to divide it by. Okay, fine. Since here we are doing all length to 1, so that means we have not really divided by L. So that's why at the end we are divided by the actual length. So it's fine now. So this is another way of calculating the stiffness matrix. This is the second way. So that we have done. And once we have the K and assemble it like this. Yeah. And after assembly, now we are solving it here. The way we did. Yeah. And we find out the stress, the reaction forces. They have the strains and stress to calculate, and we did the same thing. See here. Yeah. Okay. So here there is some other way, actually some of the transformation matrix we defined, where this related way. If you see, this is 2, 4 matrix. So local, you can also have such that the 2 by 1 related to 4 by 1 so like the same thing basically, but in case the original way that we have in the previous problem, so you can use that kind of thing as well. So you can just and this is like question. So yeah. You guys with me?
Yes, sir.
Yes, sir.
Yes, sir.
Yeah, okay. Sorry, there's some network issue. Sorry guys, network issue. So let me try again. Yeah, okay. So we are running problem number 23, 2.3, sorry. And if you run it,
Sir, we cannot see the screen. Yes, now it is coming now.
okay now?
Yes, sir,
Is it
it is
okay now?
good now.
Yeah, okay. Yeah. So so problem 2.3. So now if you see, get all the U, this case, the forces, including the reaction forces, you get the strain values for the four elements and stresses, and so we got this. Other problems are also there. To trust these, but still in the Scilab mode. So you see double slash, plus a style commenting, which is used by Scilab. So we can change it. So in front of you, we can do it. So let's replace double slash. Got a lot of issues, so I think let us start here, so this is a disturbing, so anyway it's not useful. So and I think we are done already.
Now it's visible.
Just yeah, is it okay now, guys?
Yes, sir.
Sorry. I mean, today is a really very bad network. Yeah, so this is and also I've been getting calls, and also there's a dean's committee meeting going on. So because of that, I've been getting some calls from academic section as well. So okay, so this problem number 2.7, okay, and this is we solve using the Scilab, but today we will, okay, we have replaced already with okay, just a minute. Okay, so we have this, we are solving it differently now. If you see that in this we are writing everything as a function, and everything is like a function, and then at the end we are just using a few things which is recalling those functions. So many functions are written there. Yeah. Also, there is a difference between how the function is defined. So in Scilab, you have a function, and then you will have this argument and all, and then you say end function. But in MATLAB, you don't say end function, you just say end, and it's good. Yeah. And similarly here, function t, so we will change this one to end function, end the function to end, then function to end, end, it's like this. Yeah, so what is this? Length, angle, global k, stress. Okay, so now there are a few things that like displacement, this function is not as a part of MATLAB. So these we can get rid of, sigma equal to this. All these things we will, because we don't need this. Okay, now let us try to do it, and whether it works or not. Truss 27, truss 27. Yeah, this statement is not inside any function. It follows the indeterminate definition of function stress. So what we will do is we will use these things first, and at the end we will keep the functions. So there is a certain style in every programming language. Like MATLAB is to be very flexible. You can write anything anywhere, like function you can write anywhere and all. However, this is not the same thing in other programming languages. So here now I'm putting all the functions at the end, and these are in the beginning, so maybe it will work. So let us see. Yeah, so something is going on. Okay, so we are also plotting some figure and all, so we will see. MATLAB 922. Property ISO for class MATLAB access undefined. So for plotting, we have something which we used in the Scilab. So this is we have to find out the equivalent thing, but I have commented for now. So let us see now. Too many arguments. Okay. So line. Okay, so this attend to we have to write, because in MATLAB there's some basic differences in two. So I think it's working now. I think something, yeah. So Finally, the things are working. Because of course figure okay, so there's some problem in figure, but we can fix it later. But this problem also, what we are doing, we can quickly go through it. This is problem number 2.7. This is a big problem. You can see that XY, that a connectivity matrix, so many nodes are there. Yeah, and then you have the connectivity matrix, and then we are solving it. We are also trying to plot it. So by this one, so somehow he did not plot it right, so I will change it and accordingly send you. But we are trying to here use lot of functions. So function 1, function 2, function 3, function 4, function 5. For sigma we have function. So we used lot of functions in the main program. The main program at the top and then followed by 5 functions. I'm just accessing those functions and doing it. So different way of doing all those things, but still you can find out all the values, and those values like u you can find out, sigma you can find out, f you can find out, right? So you can use u. So this gives you, because it had a lot of degree of freedom, so you have these values. Then reaction forces, all the reaction forces, and then sigma. So sigma, we have sigma like that. Okay. We have one more which I will edit actually, this truss 2.8 problem, and this also I will fix it and I will send it. So I will send you 4 files which relate to 4 truss problems in the example, and you will see how to solve them. Yeah, so I will share with you. Okay, so any question, guys? Okay, if there is no question, okay.
Sir, good morning, sir. This is Amit.
Yeah.
Sir, actually, I do not have that textbook that you are following for this MATLAB. So, how can I get that textbook that you follow? You had mentioned some J-fish you are following for this course.
Yeah, you send me an email, man. Okay.
All right, sir. Okay.
Yeah.
Thank you.
Okay then. We'll see you next week then. Okay, see you on Monday.
Thank you, sir.
Thank you.
Thank you, sir.
Thank you, sir.